I cooked up this problem with two tanks, and I think it's pretty interesting. I hope you enjoy it. What we have is a large tank and a small tank, and water is entering into the large tank initially. It gets well stirred, and then it drains out of here into the smaller tank. It gets well stirred, and it drains out. And the rate of flow of the water is constant, so there's 2 gallons per minute coming in, 2 gallons per minute coming out of here into this tank, and it drains at 2 gallons per minute. So the water levels will stay the same in both tanks. And of course the first tank I'm showing has 200 gallons, and the second tank has 100 gallons. Alright, well, I've let Y of t represents the pounds of salt in the first tank, or solution, doesn't have to be salt, but I'm just using salt here. And Z of t is the pounds of salt in tank 2. So as you might imagine, there's going to be 2 differential equations involved here. In the first case, we have water coming in at 2 gallons per minute, and the concentration is 1 pound every 2 gallons, or 1/2 pound per gallon. So if we multiply that out, that means that salt is entering this tank at a rate of 1 pound per minute. And at what rate does it leave the tank? Well, water is flowing out at 2 gallons per minute, and the concentration of the salt in this tank will be the amount of salt, Y of t, divided by 200 gallons. So the gallons units cancel, we have pounds per minute. Alright, so let's go ahead and set that up. We have the rate of change of salt in tank 1 will be Y prime, is the amount of salt, rate at which the salt enters the tank, 1 pound per minute, minus the rate at which it leaves the tank. And here the 2 cancels the 200, so I have 1 over 100 times Y. 1 over 100 Y. Alright, now I neglected to mention the initial conditions in this problem are that at the beginning this tank contains 10 pounds of salt, and this second tank contains 20 pounds of salt. So as you can see, the concentration in this tank is actually going to be 4 times the larger tank initially. And we want to see what happens through time here. So there's Y prime, my first differential equation. Now over here, the rate of change of salt in tank 2 with respect to time is Z prime, and Z prime will be the amount of salt coming in. Well, the amount of salt coming in is, guess what, it's this calculation right here, 1 over 100 Y, because it's, you know, going out and coming in at the same rates. And then so the amount of salt coming in is 1 over 100 Y minus the amount of salt going out. And the amount of salt going out will be 2 gallons per minute times Z pounds over 100 gallons. And so that is going to be Z over 50. There we go. So we have 2 different equations here. You might think of it as a system of 2 equations. Y prime is 1 minus 100th Y. Z prime is 100th Y minus Z over 50. And I pondered about putting these together. If I added these 2 equations together, this term will disappear, and we'll end up with Y prime plus Z prime equals to, what would it be, 1 minus 1/50th Z. And I don't know how to solve that, so especially with anything we've discussed up to this point. So I think my strategy here is to solve for Y in this equation, put Y over here, and then I can solve for Z. And my ultimate goal in this problem, if I failed to mention it, is I want to know what's the amount of salt in the second tank at time t. And because I think that equation is going to be kind of interesting. For example, when you look at the end game here, eventually this tank is going to contain 100 pounds of salt, because the water is flowing in at 1 pound every 2 gallons. That ends up being, eventually, as t goes to infinity, this tank goes to 100 pounds. This tank, however, will go to 50 pounds at this concentration. So we expect as t goes to infinity, this function will go to 50 pounds of salt. Again, the same concentration of 1 pound per 2 gallons. And so initially, this tank has a lower concentration than the second tank. So at the beginning of the problem, I expect that this is going to lower the concentration in this tank, and then it's going to turn around and start moving up again, and then it will plateau off at 50. So we'll see if that works out that way. And but that's why I expect that this tank having a lower concentration initially is going to lower the concentration in tank 2, and then eventually, as the concentration builds up here, they'll come up to some equilibrium where they're equal, and then this tank will start adding more concentration in the second tank. So I hope you followed all that okay. Okay. Well, let's work the math. So I'm going to do some erasing here, so because I just need room to work. So let me put our initial conditions down here so I don't forget them. So y at 0 is 10, z at 0 is 20, and we have these two equations to work through. So I'm going to erase, because I don't think I need this anymore, I'm going to erase all this stuff up here and then work these equations out. I'm back, and here's the first equation I'm going to work out, and then when we need it, here's our second differential equation, because my ultimate goal is to figure out z of t, because I think that's the interesting equation to figure out. Alright, well, if I rearrange this as y prime plus 1 over 100 y equal to 1, it fits the form of the equations that we solved by multiplying by an integrating factor. And so the integrating factor would be e to this coefficient, 1 over 100 dt. And you can see that this is going to be e to the t over 100. So I'm going to multiply by e to the t over 100. And we've done this sort of thing before. We know what happens on the left side when we also multiply by dx, or I'm sorry, with dt in this case, is we end up with the differential of the integrating factor times our variable equals to this product, e to the t over 100 times 1 dt. So when we separate the differentials also, which is basically separating the variables, we end up with this situation here. And now we can integrate. So we integrate and we get just this stuff, e to the t over 100 times y equals to, this will be 100 e to the t over 100 plus a constant. So think about this. If you take this derivative, you repeat the e to the t over 100, then you multiply by its derivative, the chain rule aspect, which is 1 over 100. So this 100 cancels, leaving a 1. Okay, and then finally, I'm going to solve for y. Multiply by the inverse, multiplicative inverse, e to the negative t over 100. And we end up with y equals to 100 plus c e to the negative t over 100. Alright, and it looks like a typical exponential decay type of function here. Now the initial condition was 10 pounds, y at 0 is 10, and when I plug 0 into here I get 100 plus c times e to the 0, which is 1. So c is going to be, what, negative 90, isn't it? C is minus 90. So I'm ready to write down y at t. And let me do that up here. So here's the function which describes the salt content in the first tank. Y at t is 100 minus 90 e to the negative t over 100. All right, now to solve for z, I'm going to need to replace this y with this function. So when we do that, we'll have z prime is equal to 1 over 100 times y, turns this into 1 minus 0.9 e to the negative t over 100. So that's 1 over 100 times y. And then minus 1 over 50 times z. Okay. Now, let's bring the z terms over. So I have z prime plus 1 over 50 z equals to 1 minus 0.9 e to the negative t over 100. There we go. Now this still fits the type of equation that lends itself to the integrating factor, because it's first order, and this coefficient is a function of t. Actually, it's a constant. Oh, telephone. Cut. Okay, sorry about the interruption. It was a phone call. Our equation is, again, an integrating factor, because this function, being a constant, could be considered a function of t, and the right side is strictly a function of t. So our integrating factor in this case will be e to the 1 over 50, integral of 1 over 50 dt, which ends up being e to the t over 50. So if I multiply everything by e to the t over 50, then as usual I'll get the differential of the integrating factor times the variable equals to this term times the right side dt. So it ends up being e to the t over 50 minus 0.9. And when we multiply these, this is 2t over 100, and I'm adding exponents to negative t over 100, so it ends up being t over 100. There we go. And dt. So let's integrate all this stuff, and we'll end up with e to the t over 50 z equals to, integrate this, we'll have 50 e to the t over 50 minus 90 e to the, I forgot to write my e in there, sorry about that, make sure you put an e in there in your notes, e to the t over 100 plus the constant. There we go. So we're getting close to solving for z. I'm going to multiply everything by e to the negative t over 50 so we can isolate z. And let me do a little bit of erasing here. So what we multiply by this term, it'll cancel the e to the t over 50, leaving z, which is a function of t, equals to, here this cancels, so I have 50 minus 90, and I add my exponents here, so this is t over 100 times e to the minus 2t over 100, so this ends up being e to the negative t over 100, and then plus c, e to the negative t over 50. There we go. Finally, we need to get this constant out of the way by applying our additional condition down here. So z at 0 is going to be 50 minus 90 plus c, and that equals to 20 pounds of salt. So let's see what that ends up being. I think c ends up being 60. C is 60 here. So finally, I can write down my function as, let me just change this c to a 60 and we'll have it, won't we? There we go. So let me kind of block that off here. And I'm going to erase all this stuff here before we go farther with it. Well, we're done getting z of t, which is 50 minus 90 e to the negative t over 100 plus 60 e to the minus t over 50. Alright, now I worked this out earlier and graphed this, and the graph looks like this, if I recall right. we start off with 20 pounds and eventually it levels off at 50. And the graph dips down a bit and comes up and then goes over like so. And so there's a asymptote here because the limit as t goes to infinity should be 50 pounds, isn't it? Which is the same concentration as the water coming in, 1 pound every 2 gallons. You have a 100-gallon tank, it's going to be 50 pounds. Well, if you look at this, the limit as t goes to infinity, these two terms both go to 0, so I get 50. And if I plug in 0, I'll have 50 minus 90 plus 60 is 20 pounds. That was our initial condition. You might recall that I observed that what we should expect to see is a dip in the concentration in the second tank because initially it's taking a lower concentration from the first tank, which lowers this concentration, and then eventually it builds back up again and reaches the final concentration. So I'm looking at this, I'm thinking, well, let's ask a few questions. And to me, an interesting question is, what is the lowest concentration it reaches in this second tank, and after how many minutes? And so this is the t-axis, this is the z-axis. And so that would be the minimum of this function, which means we get to do a little calculus here. And then another one is, at one point does the concentration is rising and then it starts to slow down. And so this is our inflection point, isn't it? In calculus, this is the inflection point where the graph changes from concave up to concave down. And you might think of it as the point of diminishing returns. It's picking up a lot of concentration here and then it starts to slow down. So I'm interested in finding out those two places. I think that would be kind of interesting. So to do so, we'll need to, first of all, let the first derivative equal 0 here, because recall when the derivative is 0, that means the tangent line is horizontal. We have either a maximum or a minimum. So if I look at the first derivative of this function, first derivative is going to be 0.9 e to the negative t over 100, and then what would that be? Minus 1.2 e to the negative t over 50. Alright, so I want to set this equal to 0 in order to find the minimum. And unfortunately I'm going to need to erase the board here, but this is the first one I'm solving for, then later we'll get the inflection point. So let me erase this. So I'm going to take this equation and divide by 0.3 e to the minus t over 50. Alright, let's see what happens here. So 0.9 divided by 0.3 is 3. And this is going to be e to the what? Well, if I take this exponent and subtract this exponent, then I end up with 2t over 100 minus t over 100 is t over 100. So this is e to the t over 100. And then here, this cancels entirely. 1.2 divided by 0.3 is going to be 4. Minus 4 equals to 0. So that's my way of solving this equation. And so let's see, e to the t over 100 equals to 4/3. And if I take the natural log of both sides, then this will cancel. T over 100 equals natural log of 4/3. So t is 100 natural log of 4/3. And let's get a number on that. So 100 natural log, parentheses, 4 divided by 3 is about 28.77. Okay, now I'm going to store that number in my calculator and plug it into the z function to determine the salt content. So I have 50 minus 90 e to the Okay, parentheses, negative. Actually, I stored it as x instead of t in my calculator, so I'm using x's here. Minus x divided by 100, and then plus 60 e to the x. This is minus x divided by 50. All right, now I haven't done this calculation before, so I hope it's going to come out reasonable. 16.25. Exactly, according to my calculator. And so z is 16.25. All right, so we can answer one question here, and I'm going to write it out by erasing this stuff first. Okay, so we can make an announcement. The minimum concentration in tank 2 is going to be 16.25 pounds after about 28.77 minutes. All right, so that's interesting information. I'm kind of marvel at this came out to be apparently an exact number. At least it looks like it on my calculator. All right, so let's find the point of inflection, which is sometimes called the point of diminishing returns. And for that, I need to set the second derivative equal to 0. So let me do some erasing here. The second derivative is going to be, what will that be? So if I multiply minus 1 over 100 times this number, it's negative 0.009 e to the negative t over 100. And then this is going to be a positive. 1 over 50 is 0.02, and just to make sure I don't mess up my decimals here, 1.2 divided by 50 or times 0.2 is going to be 0.24. So 0.024 e to the negative t over 50. And I want to set that equal to 0 to find the inflection point. So, wow. Let's, first of all, how about we multiply everything times 100, 1000, to get rid of decimal places. And let's also divide by, what were we dividing by before? E to the negative t over 50. Alright, so I'm going to multiply the equation by 1000 to move the decimal places. And then I'm going to divide by e to the negative t over 50. So this comes up to be minus 9 e to the, what was that? T over 100, wasn't it? T over 100. And then plus 24, just 24, equals to 0. So e to the t over 100 equals 2. So I'm going to put the 24 on the right side, divide by negative 9. I have 24 ninths, or we could simplify that to 8/3. Now that's interesting, isn't it? Because before we were solving e to the t over 100 equals to 4/3. Now it's 8/3. And alright, so if I take the natural log of both sides, I get t over 100 equals natural log of 8/3. So t is 100 times natural log of 8/3, and let's see what that equals up to. So 100 natural log, parentheses 8 divided by 3, is about 98.08 minutes. T is about 98.08. Okay, finally I'm going to store that in my calculator and run this number into my function here, z of t. So I wonder if I can get that function back. There it is. Comes out to be 24.6875. So z is 24.6875. Now I think that's probably an exact fraction too. Let me see if I can flush that out. Custom, whoops, exit. 6875 times 40. Oops, 0.6875 times 40, about times 80. 0.6875 times 80 is 55 eightieths. So this is 24 and 55 eightieths, which is 24 and 11 sixteenths. Okay, yeah, that's not terribly important, but I just thought it was kind of interesting that the pounds of salt in the tank are apparently 24 pounds 11 ounces, which is what that would be. It appears to be an exact number on the calculator when you use all the decimals associated with this calculation here. Alright, so we can write out this result. So the inflection point is 24.6875, which is actually 24 pounds 11 ounces, which I think is kind of interesting, after a little over 98 minutes. So anyway, we could ask other questions. At what time are there 40 pounds of salt in the tank, and so forth. We can devise all kinds of questions for this. But anyway, the main thing was to solve for the equation for the second tank, and I thought the results were kind of interesting. So there we go. That's our dilution and accretion problems.